First of all, thank you for the introduction. My name is Giovanni Micheli. I'm a postdoc at the University of Bergamo, and the work I'm presenting today is a joint work with Professor Maria Teresa Vespucci from my same university, and two researchers, Gianluigi Migliavacca and Dario Sufiface from RSE, which is one of our main industrial partners. Specifically, today I will talk about equilibrium models to analyze different coordination schemes between the TSO and the DSOs for the provision of flexibility services. And I would like to start my presentation by talking about the research motivations. Our interest in this kind of project is motivated by the increasing need for flexibility services, such as balancing services or congestion management, arising from the growing shares of renewables in power systems. And in this context, distributed resources can actively contribute to the provision of this kind of flexibility, and not just locally within their own distribution system, but also for the whole transmission network. However, to do so, the transmission system operator and the distribution system operators must coordinate their dispatching actions, and potentially several and different coordination schemes may be possible, but however, these different schemes could lead to different possibilities for the exercise of market power. So in our talk, we wanted to address specific research questions. We want to identify which could be the most effective scheme, the most effective coordination scheme between the TSOs and the TSOs for the provision of flexibility services, explicitly accounting for the exercise of market power. So in order to answer to these research questions, we developed some equilibrium models which are based on the following assumptions that I will detail in the following slides. So, first of all, in our analysis, we consider a system which consists of a transmission network to which several different distribution networks are connected. And we specifically focus on a market settled in two stages, where the first stage is the day-ahead market, and the second stage is the ancillary services market, which takes place in the real time, and where the day-ahead schedule must be adjusted in order to meet the real-time values for load and renewable generation, and also in order to solve the congestion of the lines in the transmission and distribution networks. And specifically, actions in this second stage market, in the ancillary services markets, include the adjustment, so the upward and downward regulation of generation from programmable power plants, the curtailment of the generation from renewables, and the curtailment of the loads. The problem is inherently affected by uncertainty that in our analysis we represent by means of a set S of scenarios for both the real-time values of demand and renewable generation in a two-stage stochastic programming setting. Talking about the strategic behaviors of market players, in our analysis we consider that all the flexible resources, so both the programmable power plants and also the flexible loads, are managed by a limited number of market players, and we consider these market players as profit-oriented agents who want to define joint prices for all the resources that they control on the two markets with the objective of maximize their profits. And in our analysis, we simplify a bit the bidding process by assuming that these players only act strategically on prices, and in terms of quantities, they always offer the maximum available power capacity. We assess the exercise of market power by adopting like a decentralized fashion. So we consider separately, independently, each market player, and for each market player, we formulate the corresponding bidding problem as an optimization problem, where the objective, the decision variables are the bid prices to be determined. The objective is the maximization of the total expected profits, and the constraints of the problem are the equations governing the clearing of the two markets, the day-ahead and the ancillary services market. Talking about the different coordination schemes between DSOs and TSOs, in our study we specifically compared three different schemes that are the ones reported in this slide. So we first consider the scheme A, which is a two-stage architecture where we have the day-ahead market followed by a single session of the ancillary services market, which is common to all transmission and distribution resources. Then we consider a more complex coordination scheme, which is a scheme B, that is a three-stage architecture in the sense that we have different auctions, different sessions for the ancillary services market. Specifically, each distribution system operator in this configuration runs its own ancillary services market, which is restricted to the local resources for the provision of local flexibility. And similarly, the transmission system operator runs its own ancillary services market, which is, again, restricted to only resources connected to the transmission system. Finally, we also evaluate a different three-stage architecture that we call Scheme C. It's still a three-stage architecture, but the main difference with respect to the previous case lies in the last step, the ancillary services market. Here, we assume that the transmission system operator can acquire flexibility services, not just from the transmission resources, but also from the residual distribution resources after the clearing of the local markets. So in other words, in this scheme C, the distribution resources can actively contribute and support the transmission system for the provision of flexibility services. For each of these schemes, in the following slides, I will briefly describe and provide you the mathematical formulation of the resulting optimization problem. So let us start by the first scheme, Scheme A. Let us recall that this is a two-stage scheme, meaning that the day-ahead market is followed by a unique session of the ancillary services market, which is common to all resources, both transmission and distributions. In such a scheme, each market player needs to define the following decisions. For the day-ahead market, it needs to define the bid prices for generation bids from programmable power plants. And on the ancillary services market, it needs to define for every resource control 3 decisions. It needs to define the price for upward and downward regulation of programmable power plants and the price for the curtailment bids of flexible loads. In our approach, these bids are determined by solving a bi-level program, which is reported here in this slide, where basically the upper level problem is the profit maximization problem faced by the market player who wants to set the prices for these bids so as to maximize the total expected profits on the 2 markets, the day ahead, plus the expected profits on the ancillary services market. And the lower level problems here are the problems describing the clearing of the 2 markets. So as you may see, we have 2 optimization problems, the one in the pink box representing the clearing of the day ahead market, where the market operator collects all the generation bids and clears the market so as to maximize the social welfare while respecting the energy balance constraints and the technical limits on the quantities that can be accepted. And similarly here in the green box, we have the second optimization model, which describes the clearing of the ancillary services market, where the market operator collects all the regulation bids and clears the market so as to minimize the total adjustment cost, while at the same time solving the system imbalancing, imposing the network constraints, and imposing also the technical limits on the quantities that can be accepted. Let us move now to the next scheme, which is the scheme B. As I was mentioning before, this is a 3-stage scheme. So we are splitting the ancillary services markets into several distinct and separate sub-markets. We have local markets restricted to just the DSOs and local resources, and the transmission ancillary services market restricted to only the transmission resources. The decisions to be defined are still the same, so the bid prices for the different bids. This time, they are defined still by solving an optimization problem, which, however, changes because of the different clearing rules. But the logic is exactly the same. So these prices may be determined by solving a bi-level optimization problem, where the upper level is the problem of setting the prices so as to maximize the total profits, and the lower level problems are the mathematical models representing the different markets. So the day-ahead market, the local ancillary services market, and finally the ancillary services market for transmission. Here, the mathematical formulation is exactly the same as the previous model. It only changes the fact that these models are now applied to a subset of resources. So the local ancillary services markets limits the acquisition of flexibility to only local resources inside the distribution networks, and similarly, the ancillary services market limits the provision of flexibility from and to only resources connected to the transmission. Let us conclude with the next and last scheme, the scheme C, still a three-stage architecture, but this time in the final stage, we have the possibility for distribution resources to provide flexibility services to the transmission. So the logic is still the same. Bid prices from market players can be determined still by solving bi-level programs with upper-level problems consisting in setting the prices so as to maximize total profits, and lower level problems corresponding to the different markets, the day-ahead markets, the local ancillary services market, and the ancillary services market for transmission, which now becomes an even more complex problem, because here we need to consider the possibility for both transmission resources but also residual distribution resources to provide flexibility to the TSO. As you may see, these optimization problems are all nonlinear and non-convex problems because of the presence of bilinearities, and also because of the presence of different levels of optimization, nested optimization problems, which, however, we can easily linearize. I'm not going into details because this is quite straightforward, but simply applying 3 steps using KKT conditions, linearizing complementarity constraints through the SOS1 variables, and also assume discrete bit prices, we are able to transform the original non-convex and nonlinear problem into a collection of tractable and easy to solve mixed integer linear programs. So far, we just talked about the optimization problem of single market players. In this slide, I would very quickly describe how we can get a Nash equilibrium, starting from the solution of the bidding problems of the different players. And also in this case, the approach is very simple and straightforward. And it's based just on the iterative solution of the bidding problems of the different market players and fixing the behaviors of the competitors. So basically, we start by suitably initializing the bid prices. And we consider the first market player. For the first market player, we solve the bidding problem so as to determine which is the best response in terms of prices for the player to the competitors. We update the prices of the player to the solution of its optimization problem, and we continue by considering the next player. Once all the players have been considered, we perform a convergence test by analyzing if any of the players changed bid prices with respect to the previous iteration. If this is the case, it means that we yet didn't get an optimal solution, a Nash equilibrium, so we perform another iteration of the algorithm. But once we achieve and we are able to satisfy the convergence test, we reach by definition a Nash equilibrium, because we reach a condition where no players is willing to change his bid prices, having fixed the prices set by the competitors. Talking about the numerical results, since I'm running out of time, I'm going just to summarize very quickly the main results that we got. We applied these and we tested these 3 different coordination schemes to a case study, to a benchmark network provided by the SIGRE that you can easily find in the SIGRE reports. That was a transmission network to which 3 different distribution networks were connected. We modeled the uncertainty for renewable generation and loads by means of 7 scenarios, assuming different forecast errors on both the load and the renewable generation. And we analyzed the competition between 9 market players managing different flexible resources. The results we got, I'm going to skip to the final picture, were quite unexpected. So what we observe is that the most efficient way for the coordination between TSO and DSOs was the scheme B. The scheme B that was based on the construction of local markets independent from the ancillary services market. So we noticed that with this scheme, the cost was minimized, and this result was quite unexpected because we expected that having a single market for the provision of flexibility resources, like it is, for example, in scheme A, could be more efficient, or also allowing the distribution resources to help and to provide flexibility to the transmission system would result in better results. But this was not the case. So what we observed was exactly the opposite. The best configuration, at least for our application, was to having local markets separate from the transmission system operator. And the response for this and the motivation for this lies in the congestion of the transmission network. So we observed that under the congestion of the transmission network, there are very high prices for electricity, and these very high prices for electricity may affect also the competition in local markets and may affect and may create arbitrage opportunities also for distribution resources. All the results I presented here are currently included in a paper which is currently under review, but however the preprint is available in archive and you may find the link here. So thank you very much for your attention.